morning. So our project is really about trying to advance understanding of certain fundamental processes in collisionless plasmas, such as magnetic reconnection, turbulence, especially kinetic turbulence, and particularly we're interested in how these processes interact with each other and how they affect global dynamics of such system as the Earth's magnetosphere. And in some sense, it's all about cross-scale coupling. It's coupling global dynamics in the system to small-scale microscopic kinetic physics, which may not be necessarily relevant, may not necessarily be important on large scale, but plays an important role in some sense, which I will describe shortly. And this link requires really very computationally expensive simulations, because we want to simulate large systems, but we want to also simulate small scales. And it's not just a question of, say, adapting mesh refinement, it's also a question of what kind of physics is included. So physics at small scales may be different from physics that is important at large scales. The underlying motivation for this work is understanding of the Sun-Earth connection. These processes, the magnetic reconnection, kinetic turbulence, etc., they're really fundamental in magnetized plasmas. They happen everywhere, from relatively small-scale laboratory experiments to sun, to astrophysical objects. But the motivation comes from studying the Sun-Earth connection. And that field of research is sometimes referred to as the space weather. And it's been gaining more and more attention because of the realization that severe space weather events, severe disturbances in the geomagnetic environment may have very serious consequences for the society. We are increasingly relying on power grids, satellite communications, GPS, satellites doing other things, and all of these areas could be affected by geomagnetic activity. For example, a recent study concluded that a severe storm of the magnitude that we know have happened before would inflict trillions of dollars of damage with a recovery time of several years or decades or whatever. And that motivates a lot of research in the area. And I should say that the events of this magnitude are relatively rare, but they do happen. And just a couple of years ago, we had a near miss where a huge CME from the Sun, coronal mass ejection, missed the Earth, if I remember correctly, by a matter of days. And it was of that magnitude that would inflict that damage. Okay, so what are these processes that we're interested in? One is magnetic reconnection. And magnetic reconnection is a change in the topology of magnetic field, which I tried to sketch here in a very simple way. Imagine that you have a loop, magnetic field loop, and it folds onto itself by the plasma motion and then separates into two. The reason why this is non-trivial in plasmas is that most of the plasmas that we're looking at are very good electrical conductors. In fact, they can be considered superconductors on large scales. And because of the magnetic flux conservation, this process is forbidden in a superconductor. As a consequence, the system evolves in such a way that this constraint has to be satisfied, and that often leads to accumulation of magnetic energy in the system. And not only magnetic energy is accumulated, but also there appear very narrow spatial regions where a magnetic field is highly stressed. And it is inside those regions that the microscopic physics, not necessarily accounted in this large-scale view of the problem, becomes important, breaks this constraint, allows the reconnection, and allows a relaxation which can be very rapid, sometimes explosive. And that relaxation may release the accumulated energy into plasma. So some of the most famous examples are solar prominence eruptions shown here, or magnetospheric substorms. All right. Another process is kinetic plasma turbulence. Plasma turbulence, well, turbulence in general is, of course, a huge field of research. Kinetic plasma turbulence in many ways is similar to fluid turbulence, but also differs in many in many aspects. The thing that is similar is that this general idea of energy being injected at some large scale, then cascading down via nonlinear interactions towards smaller scales where it's ultimately dissipated, that appears to hold for plasmas as well, although the nonlinear interactions and the modes that transfer energy down are different from fluids and gases. But one thing that is very different is the dissipation. In fluid or gas, the dissipation is provided by molecular viscosity. In plasmas, the direct analog of molecular viscosity, the viscosity due to binary Coulomb collisions, is very small. And so instead, the dissipation is provided by collective modes, by instabilities, wave-particle interactions, by magnetic reconnection. And this region becomes very complicated. At the same time, understanding of this region is very important, both to satisfy kind of our theoretical curiosity, but also to answer some important practical question. Turbulence is thought to play an important role in the energy balance of, for example, solar wind and solar corona, because it may provide the local energy input into the system. And if we are to understand this, then we need to know exactly which mechanism dissipate the energy, because that determines where it goes. It can go to ions, to electrons, to energetic particles, to bulk component, etc. And so to study this, we need simulations that can simultaneously include all of the processes, which is very difficult to do. So I said that underlying theme of this investigation is coupling between local and global, and what we use is are simulations that are in some sense first principle. They're large-scale kinetic models. We use I will show you results from two types of simulations, fully kinetic simulations and hybrid kinetic simulation. In the first case, we solve Vlasov or sometimes Boltzmann equation for all plasma species, ions and electrons, that is coupled to a full set of Maxwell's equations, and some of the representative parameters are here. And in the hybrid model, we give up on the kinetics of electrons, so we save a little bit of the separation of scale, but retain the kinetic physics of ions. All right. And so in what remains of this talk, I will walk you through some of the examples of the simulations that we did on blue waters, highlighting the results. We are out of compute time allocation, so what we're spending our time is analyzing data and writing papers, and I will try to highlight some of those. So this is a simulation of decaying plasma turbulence. It's a relatively simple setup. We have a cubic domain, impose a large-scale perturbation of the magnetic field on the system, and we are trying to answer those questions that I highlighted on a couple of slides before. What are the modes that transfer the energy down the scales? How this energy is dissipated, and specifically, what is the role of magnetic reconnection? Our magnetic reconnection and the current sheets that self-consistently are generated in these systems. And this movie is showing you evolution of the current density. So these bright features that appear are the current sheets. We obviously won't go into too many details, but if there is one thing to highlight, this is this plot. So what it shows is that some measure of dissipation, and so it merits a lot of discussion, but some measure of this dissipation behaves in this 3D simulation in very similar way to how it behaves in a 2D simulation. And that's hugely important because it right away rules out a lot of theories, a lot of ideas on how dissipation happens. Lots of reasons to be cautious about this. It's a first result of this kind. Its simulation has limitations. But if it stands the test of time, the test of better simulations that will come with bigger computers or more time allocation, then this has the potential to settle at least a decade worth of really hot debates in the community. I'll skip this. So this is an example of a simulation that attempts to study magnetic reconnection in a kind of semi-local model. So we really focus on the reconnection region on the current sheet, And we're studying the dynamics of the magnetic reconnection structure of the reconnection region. There has been a lot of progress in magnetic reconnection research over maybe the last 15 years, partially enabled by availability of compute power. But one of the themes that has emerged relatively recently is this coupling between magnetic reconnection and turbulence. So I already mentioned that turbulence self-consistently generates coherent structures, such as current sheets, where reconnection may happen. But the link works the other way, too. Reconnection regions undergoing reconnection inherently become turbulent as the reconnection develops. And this is very interesting, very important, again, both from the theoretical point of view, but also because it's very important to provide some kind of understanding of how a reconnection region may look like to spacecraft observations. And magnetic reconnection is an important process in the magnetosphere. In fact, it's thought to be the dominant mechanism for energy and solar wind particles entry into the magnetosphere. NASA has recently launched a dedicated mission to study magnetic reconnections called Magnetospheric Multiscale MMS. It's 4 satellites flying information, and they're trying to find these reconnection regions, understand their structures. So simulations like this are crucially important for interpretation of the data, in addition to, of course, giving us a lot of insights into the physics. All right. Well, the system where all of these pieces come together, turbulence, reconnection, in a very fascinating way, is the magnetosphere. So this is really where they couple to the global dynamics. And just to set the stage, I'm showing you here two-dimensional simulations. So on the left is an MHD simulation. It's a fluid model, does not have any kinetic effects. On the right is a simulation for similar parameters, but performed with a hybrid code, so it has kinetic ions. And you see, this is relatively smooth, well, very smooth and very laminar. And on the right, it's a very dynamic, very turbulent system, which is driven by some specific kinetic processes by reflection of ions from the foreshock. Individual pieces of physics that go into this complexity on the right are known and have been known for a while, but simulations like this, for the first time, provide a global view of the process, a global view of how various small-scale processes interact with each other, and especially of how they affect the global structure of the magnetosphere. This region here, which is dense, it's called the magnetosheath, and what we see is that magnetosheath becomes very turbulent, very dynamic, and also contains large-scale perturbations. These were 2D simulations, and one of the things that, one of the highlight of our work on Blue Waters was conducting a 3D version of that. And 3D is crucially important because in 2 dimensions, the flow profile around the magnetosphere is very restricted. And because many of the processes we're looking at are driven by the flow, ultimately, it's very important to have that flexibility, the realistic flow profile around the magnetosphere. So, and this is the global hybrid simulation that we ran last year on Blue Waters. It's really, if anything, it's really beautiful result. And our work for now is focusing on the dynamics of this region, which is called the foreshock, and that's the region where the turbulence originates. That turbulence that ultimately gets convected into the bow shock, which is here, interacts with the shock, and leads to all this large-scale disturbances in the magnetosphere. Okay. How much time do I have? 5 minutes. Okay. I will skip probably most of this. We looked at the same problem in some restricted sense also with fully kinetic simulations shown here. And that was important because the fully kinetic simulation provide kind of they are in some sense first principle. So they provide very important check for things like the reconnection and turbulence that we saw in the global hybrid simulations. This simulation is a little bit more towards astrophysics. We're simulating, again, the reconnection region, but this time we're interested in the particle acceleration. Magnetic reconnection regions could be efficient sites for particle accelerations. Skip that. I will attempt to answer these questions that were posed to us. And Blue Water's contribution, we really had a lot of help from Blue Waters. We were part of early science success program, and we had help with code optimizations. We had lots of help with the visualization, and we had lots and lots of help with day-to-day operations, data management, I/O storage, every aspect of the system. At some point we had issues with and were helped with. Broader impact, the things that we're looking at are really fundamental processes in magnetized plasmas, and they happen everywhere in the universe, so hopefully the knowledge that we gain will feed into a lot of areas. In the more kind of immediate future, they're very important for interpreting spacecraft observations, both for reconnections and turbulence and the global dynamics of the magnetosphere. Our data was used by Advanced Visualization Lab to, in this movie called Superstorms, the solar superstorms that was mentioned a few times here. Shared data. We make all of our data sets available to pretty much anybody who asks. So this is a current list of organizations that are working with our data generated on Blue Waters. The products are data set and papers. This is a partial list of papers, and there's certainly more in the pipeline. And I think that's it. I will answer questions here and maybe show this movie while I'm answering this. This is the Solar Superstorms movie that was kindly given to me.
Thanks, speaker. Thanks, Vadim. So if there are any questions from the audience? Bill, in the back. Whoop. Let's use the microphone.
So I actually have two different questions, but one is, I understand that you're working with some assistance from Nvidia and some others to actually move some of the applications to using the XK nodes, the GPUs. Can you comment on how that's going? And because these results were all on EXE nodes. So.
That's right. So it's a single person effort, and the person responsible for this is Kai Germachevsky. He's made quite a lot of progress. I don't know how qualified I am to answer this. So from my perspective, we are in a situation where we can run 2D simulations, and he's actively working on extending it to 3D. So last time I spoke with him, he said there's no problem, and that should be done very soon. It's a different code, so it's not the code that we used to conduct this simulation. It's a completely different particle and cell code.
So on that code, what role does that play then in your achieving the science projects or science goals that you have? What code?
We have not used that code in our work, in that type of work. It has been used in some other areas. It has been used in, for example, to run a lot of simulations of reconnection in the laser fusion context. Well, let me say laser matter interaction. But this is one of the directions that we want to move. So we want to move some of our science load to this code because it.
So, and you also mentioned the data sharing and that your data is available on request. How do people know to find or what the data is? How is that data discovery done if they don't happen to know you personally or something?
That's a very good question. Basically, they either hear our talks at conferences, and we try to go to as many as we can, or they read our papers. So usually as soon as papers come out, we get requests for data. We're very happy to share it.